Hi everyone, welcome back to Math 256. This is Scott, and let's get started. 1.2 is the section of the day, and that has to do with a particular kind of differential equations that we can solve just using the techniques of Math 252. So these are integrals as general and particular solutions. All right. So as the title probably spoiled for you, what we're talking about here is differential equations that can be solved merely by taking integrals. Now, in order for this to work, we have to have a very specific lineup of events. In particular, the easiest kind of differential equation to solve is one like this. So the easiest category of differential equation would be anything where what we have is the derivative of y with respect to x purely as a function of x. So the only thing over here is just involving an x, no y. So if this is what we're talking about here, then what we're talking about is the derivative of y with respect to x being a function of x. We can get to the bottom of this by merely anti-differentiating. Then we can integrate to find the general family of solutions and once again we are going to have a parameter and now the parameter is going to be nothing more than the constant of integration. Alright, let's see what this looks like. So for example, to take a relatively easy case, let's start with dy dx is equal to just something simple like x minus 3. So what we have here is the derivative of y with respect to x is nothing more than a function of x. Which means that if I want to anti-differentiate it, that'll get me to the y. Once again, what we need here is that this side involves no y's at all. Nothing involving y. Alright, well, then what that means is that y is going to be the integral of x minus 3 with respect to x. And that is going to be x squared over 2, or 1/2 x squared, however you prefer, minus 3x. Remember, we're taking the antiderivative here, so the power rule works in reverse from the typical derivative version of it. But then, because this is an indefinite integral, we have a plus c. So this gives us the family of solutions to this particular differential equation, all parameterized by this constant of integration. Now, if we wanted to pin down that constant, we would need, as we did before, to have an initial condition. So, let's throw that on. So as an example, solve the initial value problem, and we'll once again just take as our starting place the same differential equation, dy dx is equal to x minus 3, and now we're going to take as an initial value y of 0 is equal to, or sometimes you might see it as y naught, also very common, and we'll just say is equal to 7. Now this is particularly easy in this case because what that means is, well, we already know how this is going to shake out. It's going to shake out into this x squared over 2 minus 3x plus the mysterious constant of c. But now plugging in 0 for all the x's and setting the result equal to 7, what we get is which leads us to c equals 7, which gives us the solution y equals x squared over 2 minus 3x plus 7. Now, sorry, there you go. All the stuff I was saying, there it is. Now this is as easy as the right-hand side is to integrate. Now remember, integration is not always necessarily such an easy matter, but when you can do it easily, then this will give you an easy solution. Now let's look at another example and see if we can remember how to integrate it. So another example here, let's take dy dx is equal to, let's say, 1 over 1 plus x squared, and then let's take as an initial condition y naught, or y of 0, is equal to, I'll just say 0. Alright, now when it comes to integrating something like this, so first off, actually, let's make sure that we're even in the right vein of functions for this approach. We need to have a pure function of x over here, nothing involving a y. Alright, check. Now, we need to integrate this. Now, before going crazy with using some sort of a natural log or some kind of power rule or something like that, you have to also remember some of the lesser known derivatives / integrals that you might remember from your tables of interesting values back in calculus days. So this one is famous. What is it? So 1 over 1 plus x squared. This is famously the derivative of the arctangent. So what that means is that y is equal to the arctangent of x plus c. Arctangent, also written sometimes as tangent minus 1, which you would pronounce as tan inverse or tangent inverse, sometimes even a tan in some contexts, but I'll write it usually as arctan. Okay, well, this is the antiderivative of that. This gives us the family of solutions, but now we need the particular solution that we get when y of 0 equals 0. So first off, what is the arctangent of 0? Well, let's just quickly, without having to look it up anywhere or anything like that, or plug it into any calculator, let's just remember, first off, what the actual arctangent is. You give it the tangent, it gives you the angle in radians. And here, the tangent we can think of on a unit circle as meaning the slope of the ray. Now, arctangent always gives its answers on the right side of the unit circle, everything from negative pi over 2 to positive pi over 2. And we are looking for the angle whose slope is 0 on the range negative pi over 2 to positive pi over 2. And that's going to be at an angle of 0 radians. So this will be 0, which means that c is 0, which means that y is just going to be straight up arctan x. Alright. Now, let's look at a very specific and fun application of this, which is coming to you from the world of physics. All of the best examples in differential equations tend to come from physics or some related field. And in particular, let's look at the whole family of functions that we get related to velocity, acceleration, position, and so on. So the velocity and acceleration. So here are the symbols we're going to be using. So x is going to stand for the position as a function of time. We're going to use v for velocity, also as a function of time. And a to stand for the acceleration. Once again, as a function of time. All right, well, then if x of t is going to be our most basic formula here, then let's think about what it will be as we go down the differential ladder. So from x of t, we take the derivative and we would get v of t. Velocity is the rate of change of the position, so that means that v of t is going to be dx dt. But then the acceleration is how fast the velocity is changing. So that's going to be dv dt, which is in other words the same thing as the derivative with respect to time of dx dt, which, if we write it in the typical Leibniz notation for a higher derivative, is going to be d squared x over dt squared. All right, now, while we are talking about the typical sorts of physics context, such as a projectile under the influence of gravity somewhere near the surface of Earth, then what's going to be happening is that the acceleration will be a constant. This was actually discovered by Galileo for the first time, and it's a fact that is true provided that you are somewhere close to the surface of the Earth. As long as you're not changing your distance from the center of the Earth by too much, it'll be true. So here, if we assume that the acceleration is going to be a constant, and here specifically we're going to orient all of our motion in an upwards direction, which means that the acceleration, being a downwards force from gravity, is going to be negative, and then g is going to be the constant of gravitation, which in the case of Earth would be 9.8 meters per second. In the case of some other planet or moon, it would be some different number. But here we're going to assume that this is constant. Now, one way, by the way, that we are going to commonly represent constant functions in this course is going to be with a triple equals to indicate that not only does it happen to equal this, but it always equals this. So this is sometimes pronounced identically equal to or constantly equal to. So this is going to be a common notation that we're going to use to mean constantly equal to. So it's going to be a way to distinguish between a function that happens to equal something at a particular time versus a function which is constantly equal to a value. Okay. Well, if that's the case, then what we know is that the derivative of velocity with respect to time is also equal to that negative g. But here, what we have does not involve the v at all, or any other variable, or any variable at all for that matter. So we can consider this to be a constant function of time, which means we can take the antiderivative of both sides in order to get v. So what that means is that v is going to be the antiderivative of this with respect to time, that being the variable here that we were differentiating with respect to here, so anti-differentiating with respect to over here. And because this is a constant, what we're going to get is negative gt, and then plus a c. Now, what the role of this c is going to be in this case is that when t equals 0, this whole term will disappear, and this will be all that's there. In other words, c is going to be the same as the initial velocity, which we will frequently write with a v0. So, what this means is that the velocity is equal to negative gt plus v0. So this is a formula that's very familiar to everyone from the world of physics, I'm sure. But basically what it's saying is that the velocity will be, at some later point in time, whatever it started at, and then minus how long it has been going times however much it has been decelerating in this case. Okay, but velocity itself is known to us to be a derivative, and so what that means is the derivative of x with respect to time is equal to negative gt plus v0. And once again, what we have on the right-hand side is purely a function of the variable t here, which is the independent variable, the variable that, with respect to which we were differentiating. And so now we can once again solve this differential equation by nothing more than a mere integration. So what that means is that x is going to equal the integral negative gt plus v0, and that integral is all with respect to t, and that's going to give us negative 1/2 gt squared, and then plus v0 t, but then plus some constant. Now, sometimes if we have already, in a line of reasoning, used a constant of integration, we might want to be extra cautious and disambiguate them by writing maybe a subscript. Call this C, and then this one C1 or C2, or maybe D or something else. Or if there's no danger of confusion, you can just hit the reset and pretend like C was totally free and not even worry about it. And that's what I'm going to do here. I'm not even gonna notice that I'd already used C up there. However, if it bothers you, if you want to be careful about it, you can call this C1, C2, and in fact, just to assuage the concerns of any of you who might be worried that C has already been claimed, we could call this C2 and have no possibility of confusion. Anyway, continuing along here, let's think about what this C2 actually represents. Well, once again, if t equals 0, that will disappear, that will disappear, and all that will be left is that. And so that is actually just going to be the initial position. And so C2 is going to be the same thing as the initial x value, so x0. And putting the pieces together, what that means then is that x is going to be equal to negative 1/2 gt squared plus v0 t plus x0. So what we have here are the classic equations of motion that you may have seen in a physics class, all treated as differential equations, and in particular, the easy kind of differential equation you get when the right-hand side is nothing more than a function of the independent variable. Alright, well that's all there is to say about that particular section. So, thank you, and I'll see you next time.